Hello, in this video I'm going to give a quick intro to exoplanets, aka extrasolar planets. So these are planets that are outside of the solar system, planets orbiting other stars, stars that aren't the sun. And these started being detected in the 1990s. I mean, astronomical equipment has come on in leaps and bounds since the early days of astronomy, and now the equipment is good enough and the techniques are sophisticated enough that we can start observing and detecting these planets that are orbiting other stars. Since the first confirmation in the early 90s of exoplanets, there have been over 6,000 more. I mean, I lose track, the numbers are going up all the time of how many of these planets have been identified, all of them inside the Milky Way so far. The observational techniques haven't become that good that we can start detecting them in other galaxies, but that's still thousands of them inside the Milky Way, some of them pretty close, Proxima Centauri included. This is the closest star to the sun, for about 4 and a bit light years away, 4.25 light years, something like that. And there's been a planet observed orbiting Proxima Centauri. So yeah, there's been a lot of movement in this, and there's particular interest in planets in what's known as the habitable zone, the Goldilocks zone in inverted commas, where there could be liquid water. But as usual, let's go back to a brief bit of history on this. So if we go back about 100 years, 1917, there's this weird star, Van Manen 2, a nearby white dwarf. And the spectrum of this star looks like, quite a lot like, in fact, a main sequence F-type star. Now, nowadays, it's thought that this is dust falling from a planet that's getting ripped apart by this white dwarf. So it's adding these extra features to the stellar spectrum, making it look like an F-type main sequence star rather than a white dwarf. Of course, no one knew this at the time, but it was an observation that wasn't, no conclusion was drawn from the observation. The observation was accurately made about this star, and this was evidence that it has a planet orbiting it, but it's taken a while for people to conclusively say that, yes, actually, that is what we're seeing here. That is the conclusion that we're drawing from that evidence. Now, the first confirmed detections were happening much later on. So you go to 1992, there was the first confirmation of an exoplanet. This was orbiting around a pulsar. 1995, 51 Pegasi, so a star in Pegasus, and this was the first main sequence star that had a planet confirmed to be orbiting it. So this is pretty recent, 1995, we're only looking at 30 years ago, and a lot has happened since then. There are numerous methods for detecting these exoplanets. A lot of them are quite similar to the techniques used for binary stars. We've still got something orbiting something else. So, there's a lot in common with binary systems. So we start off, let's run through a few of them. You've got direct imaging. This is a problem for all manner of reasons that are pretty obvious, I would imagine. You've got a problem of brightness. This is the trouble. Okay, astronomical equipment has improved a lot. The light gathering power of telescopes has increased massively in recent years. But really, if you're going to do direct imaging, you need large planets, so things larger than Jupiter, which are a significant distance away from the parent star. Otherwise, you just can't see them. They get swamped in the brightness of the parent star, or they're too small to actually pick up the brightness from the actual planet. So that's one option, direct imaging. Then we've got the transit method. So this is like eclipsing binaries, if we're thinking about binary systems. So you've got a planet that's passing in front of the star, and then you get a magnitude drop. So we've got the same issue that we had with binary stars, that you want to have the orbital plane. We need to be looking in the right direction. You need to have the right orientation of that orbital plane. Otherwise, the planet won't transit in front of the star. If we're looking in the wrong, the wrong orientation, we just don't see that transit. We don't get the magnitude drop. Again, so this is better with larger planets. You're going to get a bigger change in the magnitude if you've got something bigger which is eclipsing across it, which is transiting across the parent star. That will also give us information about the size of the planet. Yeah, we'll be able to see in terms of the variation of the magnitude what the radius of the planet is. So that's another one that's good if you've got a large planet and a star whose magnitude is going to be affected significantly by the transit. We got the Doppler method, which again we had for binary stars. This is where we're looking at the stellar spectrum, and we're seeing, you know, if you've got a low mass star in particular, this is good for a low mass star with large planets. Although we won't have the same magnitude of motion of the star as you would get for two stars in a binary system, you're still going to have the parent star moving around the center of mass of the system. So if you've got a pretty large planet and or a low mass star, then you're going to get Doppler shifts in the star because the star is orbiting the planet just as the planet is orbiting the star. Now, the greater percentage of the mass that's in the star, the less it's going to be moving. But if you've got a low mass star with a fairly large planet, you're going to get some measurable Doppler shifts in that star as it moves around the common center of mass of that system. So Doppler method can certainly help. But again, you can see all three of these so far, unsurprisingly, this is better for larger planets. They have more of an effect. They're easier to pick up on direct imaging. They have more of an effect when they transit the star. They have more of an effect on the Doppler shift of the parent star. So larger planets, surprise, surprise, are easier to see than smaller ones. I mean, it's just obvious, really, but at least we can contextualize it in these methods. You get transit timing variations. This is another one. So we're coming back to having systems where we're looking at the right orientation. So we're getting these transits happening. But you might have a planet which we can see is transiting the parent star, but the timing of the transits isn't exactly what we'd expect if it was just one planet plus parent star. So if you've got variations, unexpected or unaccounted for variations in the transit timing, then this is evidence for other planets being there. So it can help us unpick systems of planets going around a particular star. So that's an interesting method as well. You get loads of other things as well. You get things like gravitational lensing and other such methods. So there's quite a lot of options for detecting these planets, and different methods will suit different systems of planets, you know, depending on size and type of star, size of planet, etc. Now, most of the detections that have been made are around F, G, K type stars, that sort of thing. You know, these are main sequence stars similar to the sun. Remember our spectral system, one big apple flattens giant killer monkey. So we're looking at these stars here. These are the fairly mediocre average sort of stars. You know, the sun is a G star. So these are our main sequence, not that big, not that bright stars. That's where we're getting most of our detection, and mostly for larger planets. For some of them, it's got to the extent now where scientists are actually detecting atmospheres on these planets. So it's getting that accurate. But this is a small but significant number of them. And that can then give information about the composition of the atmosphere, the temperature of the atmosphere. And this is all feeding back into this idea of the habitable zone. It's of particular interest, isn't it? If we're going to continue for billions of years as humanity, you know, we're going to go all sci-fi on ourselves, go off to another planet somewhere, or just come into contact with aliens or whatever it may be. If we're going to find life outside the solar system, then we need planets in the habitable zone, as far as we know, because as far as we know, life requires liquid water, if nothing else. So the habitable zone is where liquid water could be found, and this is going to depend upon the star and the atmosphere. the size of the planet, the rotation rate. There's all manner of things that are feeding into this. It's handy to look at things that are similar to the sun, because we know what sort of conditions around a sun can give rise to a habitable zone. But it varies a lot. I mean, look at atmosphere, the effect of that when we were going through the planets. Venus, pretty much the same size as Earth, not that much closer to the sun, but look how hot it is because of the amount of CO2 in the atmosphere. Similarly with Mars, a little bit smaller, not much atmosphere there, but potentially be more habitable. Okay, it doesn't have liquid water, but we know that it's got ice on it. So there's a lot of effects from greenhouse effects and the thickness of the atmosphere and such like. So there's a lot of work that's now going into that, of unpicking these atmospheres. Of course, you can make predictions even if you can't get any kind of direct evidence of a particular atmosphere on a planet. You can make inferences based on the distance from the parent star and the size of the star, temperature of the star. If we got a main sequence star and we see a planet which is similar in size to the Earth at a similar distance, then it's not insane to start thinking, well, maybe this is going to be a good candidate for having life on it. So so that's exoplanets. It's a very fertile area of astronomical research at the moment, as you can imagine. It's only been going 30 years or so, and great strides are being made. So exciting times.